Classifying critical points, part 3. Using the second derivative to figure out if critical points are local maximums, local minimums, or neither. So if we want to use the information from the second derivative to talk about critical points, that means that we are likely going to have to calculate the second derivative if we don't already know it. So consider the function f of x equals 4x cubed minus 6x squared minus 72x plus 12. Now, we know from earlier that the first derivative is 12x squared minus 12x minus 72, and if we factor that down, we get critical points at x equals 3 and x equals negative 2. But how can we use the second derivative to determine if these critical points are local maximums or local minimums? So remember, if the second derivative is positive at a point, then f of x, the original function, is concave up at that point. And if the second derivative is negative at a point, then the original function is concave down at that point. So that's describing what the original function is doing. And we had tests using the original function that we can map directly to the second derivative. So if we plug a critical point into the second derivative and it's positive, that means that the original function was concave up and that critical point would need to be a minimum. Now, if we were to plug our critical point into the second derivative and it was negative, that means the original function was concave down, and that would make your critical point a maximum. Let's look at what happens here. So the second derivative of this particular function is going to give us 24x minus 12. Now we need to plug in each of our critical points to see what happens. So first let's plug in 3. So if we plug in 3 into the second derivative here, we're going to get 24 times 3 minus 12, which is going to give us positive 60, which means that when x equals 3 and we're at our critical point, the original function is going to be concave up because it's positive at the second derivative. And if it's concave up, that means that x equals 3 is a local minimum. Similarly, if we were to plug in negative 2 into our second derivative, we would get 24 times negative 2 minus 12, which would give us negative 60. If the second derivative is negative, we're going to be concave down at that point, and therefore negative 2 is going to be a local maximum. So when we take these ideas about concavity and we pair it with what we know about critical points, we're able to come up with the second derivative test. Let's see how that's written. Suppose that p is a critical point of f of x. If the second derivative is positive at p, that means that the original function is concave up and that your critical point is a local minimum. If the second derivative is negative at p, the original function is concave down, and therefore your critical point is a local maximum. And if your second derivative is 0 at p, that means that this test is inconclusive, and you should do one of the other tests to determine if you have a local maximum, minimum, or neither. Now, of all the tests, this one's a little counterintuitive, because again, if your second derivative is positive, that's going to equate to a minimum. And if it's negative, it's going to equate to a maximum. So this is a really important one to keep straight as we test our different critical points. So let's look at our examples. Example 1. So we had 3x squared plus 6x plus 1. And we want to use the second derivative test to determine if the critical points are local maximums, minimums, or neither. So my first derivative was 6x plus 6. And I was able to use that to find my critical point is negative 1. If I now go ahead and calculate my second derivative, the derivative of 6x plus 6 is 6. Now, it's a little strange because I don't actually have an x to plug negative 1 into. However, the second derivative is going to be 6 for every single point, which means the second derivative at 1 is also 6. So I can still use this test. Since 6 is positive, that means that the original function is concave up, which means that x equals negative 1 is going to be a local minimum. And again, I know it's a local minimum because my second derivative is positive at x equals negative 1. Let's try another. Suppose that f of x equals 2x cubed minus 3x squared minus 36x plus 14. Use the second derivative test to determine if the critical points are local maximums, minimums, or neither. So our first derivative is 6x squared minus 6x minus 36. From there, we're able to find that the critical points are x equals negative 2 and x equals 3. Now, to use our second derivative test, we need to find the second derivative of this function. So here, that's going to give me 12x minus 6. Now that I have my second derivative function, I need to plug in each of my critical points. So let's start by plugging in negative 2. If I plug in a negative 2 here, I'm going to get negative 30. So if my second derivative is negative at a point, that means that the original function's concave down, so I know that negative 2 is a local max. Similarly, I can test my other point the same way. So if I plug in a 3 into the second derivative, I get 12 times 3 minus 6, which is going to give me positive 30. If my second derivative is positive, that means my original function is concave up, and my critical point is a local minimum. So I have a local minimum at x equals 3. So I'm able to classify my critical points by observing what the concavity is at that point. Now, the last two examples, the derivative was relatively straightforward, so the second derivative test was a good idea. But for the next couple of examples, we'll see how difficult the second derivative test can be if you have to take the second derivative of a tricky function. Example 3. Suppose that f of x is x squared over x minus 2. Use the second derivative test to determine if the critical point of f of x is going to be a local max, a local min, or neither. So remember, our first derivative, once we simplified, was x squared minus 4x, all divided by x minus 2 squared. We're able to find critical points at x equals 0, x equals 2, and x equals 4. If we want to find the second derivative of this function, we're going to have to use another quotient rule, where we set f equal to the top of our function, which is x squared minus 4x, and g equal to the bottom of our function, x minus 2 squared. From there, we need to find each of their respective derivatives. So the derivative of x squared minus 4x is 2x minus 4. In order to find the derivative of g, we need to use a chain rule, where our z here is going to be x minus 2. So our dz dx, the derivative, is just going to be 1. So the 2 comes down, and we subtract 1 from the power, and then we multiply by 1. But if you multiply by 1, you get the same thing back. So then, for our quotient rule, we're going to do f prime times g, which is this term here, minus g prime times f, all divided by g squared. So if you square something that's squared, it's now to the 4th power. So once you have your second derivative, you want to plug in each of your points to determine if they're local maxes, local mins, or neither. So if we plug in a 0, it all crunches down to negative 16 over positive 16, which is going to give me a negative 1. So if your second derivative is negative, that tells you that the original function was concave down and that your critical point is a local max. So x equals 0 is a local maximum. If we try the same thing with 4, and you plug a 4 in carefully everywhere on the top and the bottom, you end up with 16 over 16, which is positive 1. If your second derivative is positive, that means the original function is concave up, and your critical point is a local minimum. If we tried to plug in a 2 into our function, on the top we're going to get 0, and on the bottom we're going to get 0. So that means that our second derivative test is inconclusive at 2, and we need to use a different test to determine if it's a local max, a local min, or neither. Earlier, we graphed this function, and we determined that the critical point at 2 was neither a max or a min. So you can see here that the second derivative itself is not easy to compute, so it may not be the best test to use when you're classifying, but it can be done. Let's look at another tricky one.